this video, I'll be giving brief introduction to unimodal function and search technique methods in the optimization. So these are the two main objectives. So before coming to these objectives, defining unimodal functions and giving introduction to search technique, let me to recall what we have already done in the subject optimization, and this already has been added in my videos, link added in description. I have defined a linear programming problem. In the linear programming problem, we want to optimize a function. We can say it is a maximization or a minimization problem where we have a function f of x, or you can simply say that f of this x is a function of x1, x2 up till xn. So you may have as many as number of coordinate systems subject to the constraint gix. The constraint may be less than, they may be greater than, or they may be equal to some constant on the right hand side. And then we add a non-negative restrictions on the decision variable. Now this was the setup, or this is the mathematical formulation or model that we see for the linear programming problem. For these, we have done mostly the methods which we call it as simplex algorithm or simplex method. And there are variations of the simplex method such as big M two-phase method. Here we have also talked about the concept of basic solutions and other things. Then the another category that we can define is for the non-linear programming problem. Here also we want to optimize the function, but then this objective function may be with the constraint or without constraint. So you can say here we have without constraint, or we can have with constraint. So in case we want to have with constraint, we can have optimize f of x subject to the constraint gix. Okay, so this may be less than or equal to 0, or this may be greater than equal to 0. You can take the constants on the left hand side if we require. And for these also I have done some of the method. In case you have non-linear programming problem, when I say non-linear programming and linear programming problem, remember here all the f of x and the gix, the objective function and the constraint, they both have to be linear. And in case when we say non-linear, so either the function, objective function, or the constraint, or both, any one of them has to be non-linear. So if any one of them, function or the constraint, are non-linear, then we call this as a non-linear programming problem. Now for the non-linear programming problem, when we have this in the constraint, we either solve this using the Lagrange multiplier method or by using the KKT condition. Now this depends upon if the constraint is of the equality type, we have used Lagrange multiplier method, and if the constraints are with the inequality sign, then we have used the KKT condition. For the question where we have done the objective function without constraint, here depending upon whether the function is a quadratic form or a non-quadratic form, and then we have checked about the convexity of the function, whether the function is convex or not. Based on the convexity criteria, so there are other criteria such as how to check the Hessian matrix, so which is based on the partial derivatives. We can conclude whether the function have a maxima or minima. Now these are basically the direct methods for which we can look at the proof and the mathematical background. But sometimes there are some function for which we cannot say the function is differentiable and we cannot apply the direct method. For all those functions where the analytic methods are not valid, we apply the search technique method. And for the search technique method, we need to know what is the behavior of the function. So whether the function is increasing or decreasing roughly in some domain. So for that purpose, we require to know what is unimodal function. So we are now ready to define what are the unimodal functions. Now we can consider objective function that can be dependent on the single variable, or they may depend on multivariable. But for the simplicity, I am going to define unimodal function for the single variable. And before I define the unimodal model, let me to recall the monotonic functions. Monotonic function is defined as a function f of x which may be either increasing or decreasing, and we call this as a monotonically increasing function or monotonically decreasing function if for any 2 points x1 and x2 with x1 less than or equal to x2, we get f of x1 is less than or equal to f of x2, and in this case we will call this function as monotonically increasing. So here I'll write this as monotonically increasing function, and in case the inequality reversed, we will call this function as monotonically decreasing function. And of course this point x, we have taken it from the domain. You can define the domain to be a set of real numbers or in a whole domain. So this behavior for the function, you choose any 2 point x1 and less than or equal to x2 from the domain, and the function behavior should follow this pattern. So then we call this function to be monotonically increasing or monotonically decreasing. And now we look at the definition of unimodal function. A function f of x is unimodal on an interval a to b, x lies between a to b, if and only if it is monotonic on either side of the single optimal x star, single optimal point. Or we may say that, say on x star, we want to know the behavior at the point x star, whether the function is having a minimum value or the maximum value. Then the function behavior should be monotonically on either side. On one side, let's say if it is decreasing, then on the other side it must be increasing, or the vice versa. So you may look the definition in other way also. Or if x star is the single minima point, so here I have considered if x star is the single minimum point of f of x in the range a to b over a given interval, then f of x is unimodal on the interval if and only if any 2 points. So we choose any 2 points for checking the monotonicity of the function. And on one side we say that we have x star and x1 is less than or equal to x2. So you see that both these points lies on the other side, towards the right side of the point x star. So the function f of x1 is less than or equal to f of x2. Now on this we may say that the function is monotonically increasing. And whenever x star is greater than, so whenever you choose 2 points on the left side of the point for which you are checking the unimodal function, whether the function is unimodal at this point or not. So both these points should satisfy the monotonically decreasing criteria. So now let's see the definition in the form of the graph. We can have 3 types of the functions that I've taken here. One is continuous function, second is discontinuous function, and the third is discrete function. So of course continuous function, let me to take, say for example you have x and then you have f of x. It's a function of a single variable. There is no discontinuity and the function is behaving without any break. The function has a continuous value. For the discontinuous, say for example you again take a function x and then we take it f of x, and there are certain discontinuities in the function. And then for the discrete function also, discrete function, so you have some random points in the system and then we call this as a discrete function. Now for these categories, suppose I want to understand what is monotonically increasing and what is monotonically decreasing function. So we can look at for the monotonically increasing functions something like this. For the continuous graph, if the same way you want to take for the continuous monotonically decreasing without a break, you can decrease the function. For the discrete function, you can consider something like this one, a step function downwards. So this is also monotonically decreasing, and if I just take it upwards, so this become monotonically increasing function. This is monotonically increasing function. So now let's take a look at the continuous unimodal function and discontinuous unimodal function. So suppose that I say that this is a x and here it is f of x, and I want to check at the point x star. And let's say if this is the shape of the graph, this is some quadratic equation. And at this point, if you look at this, the function's behavior, it is monotonically increasing. So this side, it is monotonically increasing. And if I look at this side, this is monotonically decreasing. So then I will call this as a continuous unimodal function. The same thing if I look at in this graph, suppose that there is a graph something like this one, f of x, and then the function has a behavior something like this one and some behavior like this one. Now at this point, one can say you want to calculate at this point x star. This is also unimodal function, but then this behavior of the function is discontinuous because this function is not continuous at this point. But it fits into this definition that if you choose any 2 point x1 and x2 towards the right hand side, at this side the function is monotonically increasing and on this side the function is monotonically decreasing. You can do the reverse also. This is for the minimum criteria, but if you say that the function is decreasing on the right hand side and increasing on the left hand side, in that case we may find a maxima. So unimodal function behavior is actually studied mostly with respect to minimization. So that is why I have taken this particular example. Now let's take 2 more graphs for the discrete unimodal function and for the non-unimodal function. And suppose again I have considered an interval. So we must fix the interval for which we are checking. So suppose this is the discrete unimodal. You can see that from here, if we are checking into this interval a to b, this is the interval, and over this interval we are checking, we can see this is the x star, and this satisfy the properties definition that on one side it is decreasing, on another side it is increasing. So this is discrete unimodal function. For a non-unimodal function, say I am checking criteria into A and B, and in this one the function behavior is something like this one. Now you can say that if you have a point x star, so on the left hand side you can see if you choose 2 point on left hand side, their behavior one time it is decreasing, another time it is increasing. So the monotonicity is not followed here. So whenever we need to define a unimodal function, we must go back to the definition of the monotonic increasing and decreasing function and fix the interval a to b. In that interval, the function's behavior at the point should be one side it is monotonically decreasing, on another side it should be monotonically increasing, or the vice versa. Now we see why this unimodal function definition is so important while studying the search technique method, because we have a result saying that for the unimodal function, global minima and local minima coincide. So before I just go through the definition of global minima and local minima, let me to just give you an understanding what do we mean by local minima and global minimum. Let's consider a situation something like this where the graph have a behavior something like this one. And in this case, you can see that these are the point for the local minima and these are the points for the local maxima. So you can see here, these are local maximas and here these are the local minima. And of course, from this one, we can say that this is global minima. And if you fix the interval, so let's say if this interval is A to B, in that interval, if you can also see that in this interval, if you try to fit the definition of the unimodal function, so the function behavior should be either monotonically increasing on one side and decreasing on the other side. So in that way, obviously, global minima has to be coincide with the local minima. So this is why sometime when the analytic methods are not fitting and we want to do the search technique method and we are searching over certain discrete points on this interval, and of course there are ways how to we generally start by a trial point x0 and then we search for another point x1 and keeps on comparing the values, and then we eliminate the first one and select this as a better value. So this point I will explain in one of the video when I will be doing steepest descent method. So that is why the understanding of unimodal helps when you find the optimum solution using the search technique method. And this becomes really difficult when you consider a multivariate problem, because if it's a single variable function, it is easy to check the differentiability and the continuity criteria. But if the function involves more variables, then of course the problems get complicated. And so we see that whenever the function is not unimodal, multiple local optima are possible and the global minima can be found only locating the local optimas. And for this, of course, we need to first locate the local optimas, whether it is maxima or minima, and then find the best possible from those local minima and assign this as a global minima. But in case if the function is unimodal, then certainly we guarantee that the global minima coincide with the local minimum. And that is why we prefer to ensure that the function is unimodal, because in the unimodal function, as I mentioned, the global minima coincide with the local minima. Let's now look at the definition of the global minima and local minima. And of course, on the similar lines, you can write down the definition for global maxima and local maxima. A function f of x defined on a set S, so this set S is my domain, attain its global minima at a point x star if and only if f of x star is less than or equal to f of x for every x belonging to the domain. Whereas a function f of x defined on S is local minima, or sometimes we call this as a relative minima, at a point x star belonging to S if and only if there exists an epsilon greater than 0 such that f of x star is less than or equal to f of x for every x belonging to S, which satisfy this one. So this means in a particular subdomain. So you define a subinterval, and in that particular interval we are talking about its local minima. So this is why global occurs on the whole domain. And in case we want to specifically say that's a local minima, so this is in a particular interval or in a described precision we are checking. So this definition, this is valid for all those x which belongs to the domain but satisfying this interval. So in that interval we are saying that this is a local minima. So we note that if in the above definitions, if the direction of inequality is reversed, then we can get the definition of the global maxima and local maxima. So now we talk about the search methods, and as I've explained in the starting, Search method is basically evaluating the function's optimal value, a maximum or a minimum, when the analytic methods are not available. So when I say analytic methods, say for example the function is not differentiable or we do not have a derivative. So first order derivative putting equal to 0 gives us a stationary point, and on the stationary point we can validate what is the value for the second order derivative. If it is greater than equal to 0 or less than or equal to 0, we conclude about function having minima or maximum value, and this I'm saying in context to without constraint problem. But in that case also the function have a few independent variables, and maybe we can say the location of the optimal solution is quite known. So at that particular point we are evaluating. So in case we are able to calculate the stationary point, we can say the function is having a maxima or minima. But in the absence of these, we apply the search method. So search method works on the trial solution and then improving on those trial solution. So let me to first write some of the names on the search technique method, and in my next coming videos I'll be explaining in detail one of the search technique method. And then we'll look at the in the form of an algorithm, the working of the search technique method. The first common method for the search method is dichotomous search method, and before we apply these methods, there are certain requirements that the function has to be unimodal and it must be bounded in a given set of intervals. Second method is Fibonacci method, and for this also we consider an interval and start reducing that interval until we get an optimal solution. Then another famous method is golden search method. This is also reducing the given interval until we find the optimal solution. Fourth famous method is steepest descent method. This is based, sometimes also called it as a gradient method, since this is based on the partial derivative, and we look at the direction of the gradient, and based on the direction where it cuts the graph, we start from a trial point x0, and then based on the direction we find what is the next point and then try to calculate the function value. And as I've explained in the previous definition of the local minima, so in the given interval, if it satisfies the given criteria, so that when I look in detail, when I do the steepest descent method, so we'll see that in a given interval, in a prescribed error, we say that this is a given maxima or the minimum value correspondingly. When I say maximum value, we'll call this method as steepest ascent method. We want to find the maxima. For steepest descent, we say that it has a minimum value. There are other methods also when the function involves more than one single independent variable. So for the multivariate problem, we have following methods: Hooke and Jeeves method, Spendley, Hext and Himsworth method, Nidler and Mead's method. Now let's look at the basic working of the search method. So to start with the working of the search method, we consider a function f of x that needs to be optimized in, and here we start from this one. Let's say this is a trial and you might be also given an interval. So now let me to write in the first table, we start from a trial point, let's say x0 is a trial point, and I calculate the function value at this point. So this is the objective function value and this is what we compute. So now based on which of the search method we are applying, whether we are applying Fibonacci or the steepest descent, whichever approach we apply, we try to find the new one. So we find the next point x1. So basically we do not know the behavior of the graph, but yes, we know that if this at this point x0, this is the function value, and then we calculate what is the function value at x1. If whether this function value f of x0 is less than or equal to f of x1 or not. So if it is less, then we'll say of course this is minimum value then in comparative to this one, and then maybe we drop this point x1 from the interval, from the given interval. So in detail method, the detail method we can do only once we are doing a particular method, but this is the overall process of the working of the search method. So once we find the new point, we again calculate f of x1. So this we compute again the objective function at this one, and then we try to compare f of x1 with the previous value of f of x0. If the condition is satisfied by that particular search method, whichever we are applying, or if it is less than epsilon, if it is within the precision error that we have defined, then we say and we conclude about the optimal solution. If this does not satisfy our precision criteria, then we keep on repeating. We will consider this as the trial point and we will continue our iterations from here only. So this basically we find one more point x2 and then check function value at x2 and so on. So from here we keep on repeating our point. So of course from here, not from the trial point, but we start repeating from this one. So if I just simply say that this point is my xi and I'm finding xi plus 1, and then we keep on repeating. So we check between xi plus 1 and xi. So this is how the working of the search method works on by trial method. In fact, one of the gradient method which is used in the numerical analysis technique is the Newton-Raphson method. So these are very much in align with the search technique method that one apply in the numerical technique. So sometimes these are also called numerical optimization techniques. So in my next video, I'll be taking the one of the search technique method in detail.